Hello guys, welcome to the post-laboratory discussion on the 5 experiments that we performed during the midterm period. Experiment number 1, kinematics. Experiment number 2, laws of motion. Experiment number 3, conservation of energy. Experiment number 4, Archimedes principle. And experiment number 5, linear expansion of metals. Experiment number 1 again is about kinematics, and we have two parts for this experiment. The first part is to verify that the value of acceleration due to gravity is equal to 9.8 meters per second squared, and the second is to predict the horizontal and vertical distance of a ball shot at an angle. In this experiment, we have two parts. The first part is free fall motion, and the second part is projectile motion. For the first part of this experiment, so we have this setup. We can see here the picket fence. We also have the photogate head, and to connect the photogate head to the Explorer GLX, we need to use a photogate head cable, which is attached to the digital adapter. And then the digital adapter is connected to the Explorer GLX. And then to make the setup in place, we need a metal rod and also an A-base. So what we need to do here is just to drop the picket fence in the photogate head, and the photogate head will measure the position, which is the vertical displacement, and also the velocity of the picket fence. And then the position and also the velocity will be recorded in the Explorer GLX. Assuming that we have this reading after performing the experiment for the trial 1, assuming that the reading on the Explorer GLX, we have the position which is equal to 0.3, and then for the velocity that is equal to 2.42. So these are the data that we're going to use to compute for the acceleration due to gravity. So we can see here the table for part 1. So the first column is about the trial. The second is for the vertical displacement, in which this is the position which is read on the Explorer GLX. Velocity, which is the third column, and the last column is for the acceleration due to gravity. And then we can also see here that we're going to have 5 trials, 1, 2, 3, 4, and 5 trials. The theoretical value for acceleration due to gravity is already given here, and that is equal to 9.8 meters per second squared. So what we need to do is we just have to record the position under the vertical displacement, and that is expressed in meters. And then for the velocity, which is the second reading, and that should be recorded here under the velocity. So these are actually the data for trial 1. So after trial 1, we need to perform again the experiment, and we need to get the data for trial 2, 3, 4, and 5. So assuming we have this data for the vertical displacement again, so that is 0.3, for the velocity that is 2.42 meters per second, and for acceleration due to gravity, we can compute the acceleration due to gravity using this formula. Acceleration due to gravity, which is g, is equal to v squared divided by 2y. The v here is the velocity, which is in the third column, and then the y is actually the value of the vertical displacement. After getting all the acceleration due to gravity for trial 1, trial 2, trial 3, 4, and 5, we need to get the average. So to compute for the average experimental acceleration due to gravity, we just have to add the 5 values and then divide it by 5, and we can get the experimental acceleration due to gravity, and that is the average value. Again, suppose we have 0.3, which is the value for the vertical displacement, and then for the velocity that is equal to 2.42. Let us compute now for acceleration due to gravity. Again, the formula for acceleration due to gravity is v squared divided by 2y. So based on the given, the velocity is equal to 2.42 meters per second. So we have to square this and then divide this by 2 multiplied by the vertical displacement or the position, which is equal to 0.3 meters. Okay, so using our calculator, so that will be equal to 2.42 square, and then divided by 2 times 0.3, which is 0.6, and then the value here is 9.76. So the value of acceleration due to gravity here is 9.76 based on the given vertical displacement of 0.3 and velocity, which is 2.42. Assuming that the assuming that the average value here after computing for the acceleration due to gravity for trial 2, 3, and 4, and 5, assuming that we computed for 9.82, assuming that this is the average value. So we need to compute for the percentage error. To compute for the percentage error, so the formula is experimental value, which is this one, okay, minus the theoretical value, which is 9.8 meters per second squared. So this is absolute value. So meaning if you get negative value, you just have to make that positive. So this is divided by the true value multiplied by 100. So since the given is 9.82 and 9.8, so let us compute now for the percentage error. So this is simply equal to 9.82 minus 9.80 absolute value over 9.80 multiplied by 100. So the value is equal to, again, 9.82 minus 9.80 and then divide by 9.80 multiplied by 100. So the percentage error here is equal to 0.20. So this one is equal to 0.20%. Okay, so this is the percentage error. So this is the first part of the experiment. Now let us proceed with the second part of the experiment, which is the projectile motion. So for the projectile motion, so we have here the projectile launcher, the Photogate cable, which is used to connect the two Photogate heads to the Explorer GLX. And we also use here the Photogate head mounting bracket. This one is called the Photogate head mounting bracket. And we have here the ramrod which is used to insert the ball inside the projectile launcher. And we have also to connect the time of flight accessory in the Explorer GLX to make sure the time of flight of the plastic ball. So the projectile launcher can be set to different ranges. Okay, we can set this to short range, to mid range, or to long range. But in our experiment, we only need to set the plastic ball in the short range, and we also need to set the angle of the elevation or the projectile in a certain angle, and then the angle depends on the data that we're going to assign to you by your professor or depending on your choice. And also we need here a table plan, so that's to make the setup in place. So we need to launch the projectile here. Okay, we need to launch the plastic ball, okay, by just pulling the string here, and from that what will happen is that the plastic ball should touch the time of flight accessory. So once the plastic ball touch or land on the time of flight accessory, the Explorer GLX will record the initial velocity of the plastic ball and also the time of flight of the plastic ball. So from this data, so we make sure that the initial velocity is 3.08 meters per second, and the time for the plastic ball to land on the time of flight accessory is 0.7840 seconds. So again, in this experiment, we're going to predict the horizontal and vertical displacement of the plastic ball, okay, given a certain angle. So we need to put the initial velocity on the column for the TGLX, or for the VGLX, I mean, so that is expressed in meters per second. And then for the time of flight, so we have to place that on the second column, which is the TGLX, for the time of flight. So again, so this is expressed in seconds. And then for the initial velocity, which is the VGLX, that is expressed in meters per second. After getting all the data here, okay, after getting the time of flight and also the initial velocity of the plastic ball, we need to compute for the vertical displacement and also the horizontal displacement. To compute for the vertical displacement, so we have to use this formula, y, which is the calculated value of the vertical displacement, that is equal to the initial velocity, which is the VGLX, sine theta. So whatever be the angle that you set on the Explorer GLX, so that's the angle here, and then the time here is actually the TGLX, okay, minus 1/2, multiplied by g, which is constant acceleration due to gravity. So in this one, we're going to use 9.8 meters per second squared, and then the square of the time GLX. So this is how to compute for the y calculated. And then for the x calculated, we're going to use this formula, x, which is the horizontal displacement, that is equal to the initial velocity. Again, this is equal to the BGLX, which is the reading here, and then the cosine theta, and then multiplied by the time, which is also the TGLX. So the TGLX again is on the second column. So these are the formulas that we are going to use to compute for the y calculated and also the x calculated. Now the question is, how can we get the y measured and also the x measured? The y measured can be measured, okay, it can be measured using steel tape. So we have to measure the height of the plastic ball from the tip or from the mouth of the projectile launcher. So using steel tape, so we can measure the y. So that's the y measured. And then so since this is the, for example, this is the time of flight accessory, and then the ball will land here. Okay, so we need to measure the x horizontal displacement from this point. Okay, so from this point to that point, so that's actually the value of the x measured. So we now have the y measured, the y calculated, the x measured, and the x calculated. So we need to perform this experiment in 5 times or 5 trials. And then after that, again, so we have to compute for all the y measured. We have to measure the y and also compute for the y calculated for all the trials. And then after that, we have to compute for the average. Again, to compute for the average, we just have to get the sum and then divided by 5. Okay, the same thing with this one, the summation divided by 5, the summation of the x measured divided by 5, same thing with the x calculated. So this is the summation of the x calculated divided by 5. And then after that, we have to compute for the percentage difference using the formula. So the percentage difference has different formula with the percentage error. So in this one, so we have to know the value 1. So the value 1 can be the y measured. It can be also the y calculated. Okay, minus value 2. Again, the value 2 can be the y measured or the y calculated. Again, this is absolute value. If you get negative value, you just have to make that positive. Okay, divided by the average, you need to get the average now 1 and 2. So value 1 plus value 2. Okay, and then it should be divided by 2. So this is the average multiplied by 100. So this is how to compute for the percentage difference. Using the following data, so let us compute for the y calculated, x calculated, and percent difference. The time GLX is equal to 0.7840, while the VGLX is equal to 3.08. So the y measured were already given, so they were given, and that is equal to negative 1.15, while the x measured is 1.56. So let us compute for the y calculated. So y calculated is simply equal to initial velocity multiplied by sine theta multiplied by time minus 1/2 GD squared. So let us substitute all the data. Okay, so the VGLX is equal to the initial velocity. So this is 3.08 meters per second multiplied by sine. So the given angle here is 50 degrees. So sine 50 degrees multiplied by time. So time is 0.7840 seconds minus 1/2 multiplied by 9.8 meters per second squared, and then that is to be multiplied by the square of time square. Okay, so the answer here is, say, 3.08 multiplied by sine 50 and then multiplied by the given time minus 1/2 multiplied by 9.8, then multiplied by the square of time. So the y calculated here is equal to negative 1.16 meters. Okay, so guys, so the answer here is negative because the negative there is the direction. Okay, so meaning the object or the ball is going downward. So the y here is negative. Okay, again, so the y calculated based on our computation is negative 1.16. Okay, so now let us compute for the x calculated. x is equal to the initial velocity multiplied by cosine theta multiplied by t. So this is equal to initial velocity is again the 3.08 meters per second multiplied by cosine angle, which is 50 degrees, and then that is to be multiplied by the given time, 0.7840 seconds. So x calculated is equal to 3.08 cosine 50 multiplied by 0.7840. So the answer here is 1.55 meters. So this is the value of the x calculated. Suppose that we have the same given for the TGLX and VGLX for trials 2, 3, 4, and 5. So meaning our average will be also the same, and that will be negative 1.15. This is negative 1.16, 1.56, and 1.55. Now let us compute for the percent difference. The percent difference for the y measured and y calculated. So the percent difference is equal to the difference between the y measured and y calculated. So that is 1.15 or negative 1.15 minus 1.16. Okay, you can use negative or positive. And then over the average, so 1.15 plus 1.16 over 2. And then this is to be multiplied by 100. So this is equal to 1.15 minus 1.16. Again, so this one is absolute value, okay? Again, so if your answer is negative, you have to change that to positive. Divided by the average, so 1.15 plus 1.16, and then divide by 2. And then that is to be multiplied by 100. So the percent difference here is actually equal to 0.87. Okay, and then for the other one, which is the x measured and x calculated, so we just have to use the same formula, and that will be 1.56 minus 1.55 over the average of the 1.56 and 1.55. Okay, so that will be 0.01 over 1.555, and then to be multiplied by 100. So this one is actually equal to 0.64. So this is the percent difference for the x measured and x calculated. There are two guide questions. The first is the magnitude of the acceleration of a ball greater while it is being thrown straight upward or as it falls? Explain. So the first question is actually about free fall motion, in which under the free fall motion, we are actually referring to the acceleration due to gravity. So meaning in this one, so the magnitude of the acceleration of the ball being thrown straight upward is equal as it falls. And that acceleration is equal to the acceleration due to gravity, which is constant, and that is equal to 9.8 meters per second squared. For the second one, how do changes to the launch angle affects its hang time, horizontal displacement, and vertical displacement? And then the second is how do changes to the initial velocity of a projectile affect its hang time, horizontal displacement, and vertical displacement? So we can actually relate the launch angle with the hang time, horizontal displacement, and vertical displacement based on the formula that we use in our experiment. Okay, so the first formula is actually in getting the horizontal displacement, and to find the horizontal displacement, so we are using this equation. So that is simply x is equal to initial velocity multiplied by cosine theta multiplied by t. So we're going to set the initial velocity and time as constant, so therefore we can actually relate the x and also the initial and the theta. So in this one, if we're going to increase the theta, so what will happen to the cosine theta is there will be a decreasing value of cosine theta. So meaning, guys, if there will be decrease in the value of the cosine theta, what will happen to the value of x will be also decreasing. So there will be also decrease in the value of the x. So therefore, we can say that the theta is inversely proportional to the horizontal displacement. In case of the launch angle and hang time, so we can also relate the two. Again, so from this formula, we can actually derive the formula for cosine theta. So cosine theta is equal to x over initial velocity, okay, multiplied by time. Again, so this one, so this is also the equation that we use to arrive on the first answer, in which theta is equal to, or that is inversely proportional to the displacement. Again, if we're going to increase the angle here, there will be decrease in the value of the cosine theta, and then if that is the case, there will be a decrease in the value of x. So again, so they are inversely proportional. While for the angle and the time, so again, if we're going to increase the value of the angle, there will be decrease in the value of the cosine theta, and then what will happen to the time is there will be increase in the value of time. So therefore, so theta and time, so they are directly proportional. Okay, so that is relationship between the launch angle, hang time, and horizontal displacement. So how about the vertical displacement? For the vertical displacement, so we are using the formula y is equal to the initial velocity multiplied by sine theta multiplied by t minus 1/2 t squared. Again, we're going to relate the sine theta with y, okay, or the theta with y. So in this case, if we're going to increase the value of the angle, okay, what will happen to the sine theta is it will also increase. So there will be also increase in the value of the sine theta. And then what will happen to the y is there will be also increase in the vertical displacement. So therefore, we can say that increase in the angle will also increase the value of the vertical displacement. So they are directly proportional. Okay, second question is about the initial velocity and also the in relation to the hang time, horizontal displacement, and also the vertical displacement. Okay, so let us first relate the initial velocity, this one, with the horizontal displacement. So if we're going to set the theta and time as constant, okay, so we can see here that they are directly proportional. So if we're going to increase the initial velocity, there will be also increase in the horizontal displacement. Again, so initial velocity is directly proportional to the displacement. On this formula, so we can also see that if we're going to set the time and the other variable as constant, same with the angle. So we can see here that the initial velocity here, and then the y is on the other side. So we can see that they are directly proportional. So meaning if there will be increase in the initial velocity, there will be also increase in the value of the vertical displacement. Okay, so how about the initial velocity and also time? Okay, for the initial velocity and time, so we're going to use this equation. So here is the cosine theta, and again, so we have x over b naught t. Okay, but in this case, guys, we are actually relating time and initial velocity. Okay, so in this one, if we're going to compute for the initial velocity again, so from this formula, so initial velocity is equal to x over cosine theta multiplied by time. Okay, so what we say about the two? If x is constant, the theta is constant also. So here we can see that they are inversely proportional. So if there will be increase in the velocity, and then what will happen is there will be decrease in the time, okay, or it will be shorter. And experiment number 2 is about laws of motion. We have three objectives here. The first objective is to determine the mass of an object in static equilibrium. Second, determine the moments of force in an equal arm balance. And third, study second law of motion. So let's start with the first objective, or the first part of the experiment, which is about translational equilibrium. For translational equilibrium, we have this setup. Okay, we have the dynamics card, which is placed in the dynamics track. We need to use angle indicator to measure the angle. And we have here actually a force sensor. So this is used to measure the tension on the string, which is connected to the dynamics card. And the force sensor is connected to the Explorer GLX to record the reading on the tension or on the force. We need a universal clamp here and also metal rod, okay, or stand. So here we're going to apply here the first condition for equilibrium. So when we say equilibrium, so this is the state of a body in which there's no change in the motion. So we can say that there's no change in the motion if the object is at rest. So in this case, the object is actually in the state of rest. So the first condition for equilibrium actually is summation of forces on x, it should be 0, and then the summation of our y is equal to 0. So this is actually the first condition for equilibrium. The first condition of equilibrium is actually the under the translational equilibrium. So the target here is to compute for the mass of the cart, so which is equal to tension divided by g sine theta. So we need to identify all the forces acting on the cart, and then based on that, we have here the normal force, which is the force perpendicular to the surface. Also here we have the weight of the cart, and attached to the force sensors, of course, we have the string here, so there's a tension here. So we're going to draw this in a free body diagram. So the tension will be in this direction, and then we have to measure the angle also, the angle, and the normal force is perpendicular, so we have here the normal force and the weight of the cart. So we're going to rotate this one, so that will become like this. Okay, the tension will be on this axis, the normal force will be on the y-axis, and then there will be rotation on the weight with a certain angle. So this is now the weight. So we're going to apply the summation of forces on x equal to 0. So we will arrive on this formula. But anyway, we need to use this formula, summation of forces on x equal to 0. So we have to identify all the forces acting on the cart on the x direction. So these are the tension which is going to the right, so that will be positive. And then for the y, we have w sub y and w sub x. So in this case, we're going to use w sub x. So w sub x is the horizontal component of the weight, or w. So to compute for w sub x, this is w multiplied by sine theta. So this is going to the left, meaning that will be negative. Minus w sine theta equal to, it should be equal to 0. Okay, to satisfy equilibrium, the sum should be equal to 0. So to compute for weight, weight is simply mg. So therefore, we can replace w by mg. So this will become tension minus mg sine theta equal to 0. And then from that, we can transpose mg sine theta on the other side. So this will become tension equal to mg sine theta. So the target is to compute for the mass of the cart, this variable or this quantity. So we just have to divide both sides by g sine theta. So the final formula is this one. So mass is equal to tension divided by g sine theta. So we're using force sensor here to measure the force or the tension. And then on the screen of the Explorer GLX, so we can see here the tension or the force. So the tension here is expressed in Newton. So meaning if the reading is 1.32, so this is 1.32 newtons. And then this is again the tension or the force, which is read by the force sensor. We just have to place the reading on the force sensor or the value of the tension on this part, okay, on the column for the tension. And then we can see here on the second column, we have the angle, which is 15 degrees and 20 degrees. So meaning we need to incline or to change the angle of the dynamics track from 15 to 20. So we need to start at 15 degrees. So at 15 degrees angle, so the reading for the tension is 1.32. Again, so we need to compare the mass of the cart, experimental and also theoretical. For the experimental value, okay, we're going to use this formula. Okay, so that's equal to tension divided by g sine theta. And then for the theoretical value, we need to measure the mass of the cart using top loading balance. We just have to place the dynamics cart in the top loading balance, and then whatever be the reading there, so that is the reading for the mass of the dynamics cart. And then please take note, guys, that if we're going to use the top loading balance, the reading is in grams. So we need to convert this to kilograms. And then whatever be the reading there, we just have to place that here. So that will be the theoretical value. Again, the theoretical value is the measured value of the mass from the top loading balance. And then experimental value, we have to use the formula T over G sine theta. And after that, we have to compute for the percentage error after computing for the experimental and also after getting the theoretical value. Percent error is the theoretical mass minus the experimental mass over theoretical mass multiplied by 100. So let us compute this one. Again, the tension here is 1.32. Okay, again, the formula for the experimental value, okay, mass is T over G sine theta. So the tension here is 1.32 newtons over G, which is constant. This is 9.8 meters per second squared. Okay, multiplied by sine. So the angle here is 15 degrees. So this is sine 15 degrees. Okay, so the value here is equal to. Okay, so let's compute this one. So this is 1.32. Okay, divided by 9.8 multiplied by sine 15. So the answer here is 0.52. So this one is 0.52 kilograms. So we have to place the 0.52 kilograms. Again, this is the experimental value. We have to place that here. So assuming that the theoretical value, or after measuring the cart using top loading balance, is, let's say this is equal to 517.65 grams. So we just have to convert this one into kilograms. So divide this by 1000 and then round off this one into 2 decimal places. So this will be 0.52 kilograms. So this is the value. Okay, so since this is 0.52, this is also 0.52. So percentage error should be automatic to be 0%. Again, the formula is 0.52 minus 0.52 over the theoretical value, which is also 0.52 times 100, absolute value. Again, this is equal to 0. So this is the percentage errors. And then this is the first part of the experiment number 2. Okay, for the second part, the objective is to determine the moments of force in an equal arm balance. So we have this set up. We need equal arm balance. And then in the equal arm balance, we can see here that we have loop 1, okay, loop 2, loop 3, and then also on the other side, loop 1, loop 2, and loop 3. And here, this part is actually for the first column of our experiment, and then this is for the second column of the experiment. So this is for the hanging mass, and the other side is actually for the applied force. So for the hanging mass, we need to use, of course, different masses here. And for the applied force, so whatever be the reading here, using the force sensor, so that's the value of the applied force. And then since we're talking about the hanging mass here, so therefore we need to get the F1 here. And then the F1 here is actually equal to the weight of the hanging mass. So to compute for that, that is simply mass of that object, of the hanging mass, multiplied by acceleration due to gravity. And then the acceleration due to gravity here is, we're going to use 980 centimeters per second squared, because the mass here is expressed in grams. And then for the force sensor, so the reading here will be in newtons. So therefore we need to convert newtons into dynes, and that can be converted by just multiplying this one by 100,000 to make that dyne. Okay, so what we need to do here is to balance the equal arm, and on the left side we need to place here an hanging mass, and then on the second, on the other side, we need to place there a force sensor. And also we need also to compute for the R and also the angle. For loop 1, for loop 2, and for loop 3, there are different values for R and also different values of the theta. For R, okay, so this is the formula. This is Pythagorean theorem. So to compute for the lever arm, okay, or the distance from the applied force to the point of rotation, so that's equal to the square root of x squared plus y squared. Okay, the x here is actually the distance, this one. Okay, assuming we have, if this is the loop 1, so x, and then this is the y, this is the value of y. So you have the x, you have the y, you can compute here the r. And then again, this is a right triangle, meaning we can we can use the Pythagorean theorem. And then for the angle we can use tangent theta. Okay, so angle is equal to tangent or arctangent y over x. And then for the torque, so this one we need to compute the torque on the left side and also the torque on the right side. And then our target is they should be equal. So the torque on the right side should be equal to the torque on the other side to make the system in equilibrium or rotational equilibrium. So the formula to compute for torque is this one. So we have force, applied force, or the weight of the hanging mass multiplied by the lever arm and then multiplied by the cosine of the angle. So we can see here the table showing the value of r and also the value of theta given the different loops. Okay, for loop number 1, the value of r is 8.06 and the angle is 45 degrees. So where is loop number 1? Loop number 1 is here. Okay, so the length of this is equal to 8.06 centimeters and then the angle here is 45 degrees. For the second loop, okay, for the second loop, the value of the r is 12.75 and then the angle is 26.57. For the third loop, 8.02 centimeters as the value of r, and then for the theta, that's 18.43 degrees. So we need to identify the position of the hanging mass and also the position of the applied force. So wherever be the position, okay, whatever be the position of the hanging mass and also the applied force, so we need to identify the loop number, and then whatever be that loop number, we just have to copy the value of r and theta based on the given loop number. So this is actually the setup again. This left side is intended for the first table, which is the hanging mass, and then the second part or the second side or the left side or the right side, this is intended for the applied force. Again, so the hanging mass should be placed here. Okay, assuming this is 50 grams, so the 50 grams should be placed here. And then as we can see, this is 0, loop number 1, loop number 2, so the hanging mass is placed at loop number 2. Okay, and then for the right side, so the force sensor is placed at loop number 2, so that's why this is loop number 2. And then whatever be the reading here, we just have to place that here for the value of the applied force. Again, the value of F1, we just have to multiply 50 by 980 centimeters per second squared. Okay, we can get the F1. And then R1 and theta 1, so they are the values of the lever arm and also the angle. Okay, on loop number 2, so we need to look at the table showing the value of R and also the value of theta. And then torque 1, again the formula for torque, that is F R cosine theta. And then for the applied force, again, we need to copy the reading here and then multiply this by 100,000 to get the value of F2. Again, so this is also on loop number 2. So what is the value of R in theta on loop number 2? And then compute for the torque on the right side. Again, so we have to place the hanging mass 50 on this side. Again, this is placed on loop number 2. And then the reading here should be placed here at applied force. And then again, this is also at loop number 2. Okay, example. Okay, assuming that the reading on the force sensor, okay, on the right side of the equal arm balance is 0.50. Okay, assuming that is the value. So let's now solve the value of the torque on the right side and the torque on the left side. Okay, anyway, so we have this formulas. Okay, we have different values for loop, and loop number will be provided anyway, so that can be seen on the table. So the value of R and also the value of theta depending on the loop number. And again, the value of F1 here, we should multiply this by 980 centimeters per second squared. And then for the F2, you need to multiply this by 100,000 to convert the Newton into Dyne. And compute for the torque 1 and also torque 2, the formula is R multiplied by F cosine theta. And whatever be the reading for the first data or for the first table, you just have to copy that on the third column. and on the third table, and also the data on the torque on the from the second table, you just have to copy that to the third table, and then after that you have to compute for the percentage error. Guys, please take note that in this one, the theoretical value here is the table one. Okay, torque one. The torque one is considered as the theoretical value. So that's why we are computing for the percentage error. Again, the formula is torque 1 minus torque 2, absolute value divided by torque 1, which is the absolute, or which is the theoretical value, multiplied by 100. Okay, so let's try to compute this one. Okay, the given here is, okay, so mass is 50 grams. Again, we need to multiply the 50 by 980. So this is 50 multiplied by 980. So the answer here is 49,000. Okay, this is 49,000 times. And then the 50 grams is at loop number 2. So what is the value of R and theta at loop number 2? So this is 12.75. And then theta is 26.57. Now let us compute for the torque. So the formula is F1 R multiplied by cosine theta. So this is 49,000. Again, so let me write here the formula. So this is the formula, FR cosine theta. Okay, so F is 49,000 multiplied by 12.75 and then multiplied by cosine 26.57. So the answer here is 558,769.25. So let me round off this one into the decimal places. Okay, so this is for the first column or your first table. Okay, for the first table. On the second table, so the applied force is also equal to 0.50. Again, we need to multiply this by 100,000. So the value here is 0.50 multiplied by 100,000. So this is equal to 50,000. And then again, so this is at loop number 2. This is also 12.75 and 26.57. So let's compute for the torque. So 50,000, okay, multiplied by 12.75 and then multiplied by cosine 26.57. So the answer here is 570172, okay, 0.71. So this is the torque on the right side. Now I'm going just need to copy on the third table. This is 8769.25, and then the torque 2 is 570,172.71. Now let's compute for the percentage error. Okay, so this is equal to 558769.25 minus 570172.71, okay, divided by the theoretical value, which is torque 1, 558769.25, and then multiply this by 100. So the answer is 2.04. So the percentage error here is 2.04%. Okay. So this is the second part of the experiment. Now let's move to the third part of experiment number 2, which is to study second law of motion. Anyway, so second law of motion is the law of acceleration, in which under the second law of acceleration, or the second law of motion, which is the law of acceleration, so we are following this formula. So summation of force is equal to mass multiplied by acceleration. So we can say that the mass is directly proportional to the force. Acceleration is also directly proportional to the force, but acceleration is inversely proportional to the mass of the given object. So this one, so we have two objects here. The first one is the hanging mass, and the second is the dynamics cart. So they are connected by a string. And then what we're going to do here is we just set a certain distance here to the endpoint, okay, to this block or to this stopper, okay, from this plunger to the stopper. So this is actually the distance, or x. So we need to use a stopwatch to measure the time. Okay, so from this point to that point, we need to get or to release the cart. And then what will happen is, if we're going to release the cart here, the hanging mass will be also accelerating downward. So we can get the time here, and then the distance is given. So we can actually compute the acceleration here. So based on the formula for the for motion, so acceleration here is equal to 2 multiplied by x divided by t squared. Okay, this is the experimental value of the acceleration of the cart. Now, how can we compute for the theoretical value, or for the accepted value of the acceleration of the cart? So we need to treat this two objects separately, and then we need to identify all the forces acting here. Of course, again, so we have the weight of the cart, we have the normal force, in which the weight of the cart is equal to the normal force, so they will be cancelled. And this is attached to the string, so we have here the tension. So on the cart, okay, at cart, so summation of forces is equal to MA. So the force here is tension equal to, so this is the mass of the cart. Okay, let me use MC as mass of the cart multiplied by the acceleration. So this is the formula for the cart. Okay, for the hanging mass, so what are the forces? We have the weight of the hanging mass, and we also have the tension here. And then we also need to use this formula, summation of forces equal to MA. So tension is going upward, this is positive. Weight is going downward, so this is negative. And then this is equal to hanging mass. Let me use MH for the hanging mass. Okay, multiplied by acceleration. So the tension here actually is the same. So the tension from the cart is also the tension on the hanging mass. So they are equal because they are attached by one string. Okay, they are attached by one string. So we can say that whatever be the velocity of the cart, that is also the velocity of the hanging mass. And therefore, whatever be the acceleration of the cart, that is also the acceleration of the hanging mass. So meaning acceleration here and the tension on the first formula here is also the tension and also the acceleration on the second formula for the hanging mass. So what we're going to do is we just have to substitute, okay, the first equation to the second equation. So that will become, so tension is equal to MCA. So I'll be replacing tension by the first formula or the first equation. So that's MCA, okay, and then minus weight. Okay, so this is the weight of the hanging mass. So this is mass of hanging, or hanging mass multiplied by G. Okay, hanging mass multiplied by G. Okay, equal to, okay, again, so this is accelerating downward. So the acceleration here should be negative. So we have here negative acceleration. So minus hanging mass multiplied by acceleration. Okay, so what we're going to do is we just have to put like terms on one side. So that will be mass of the cart, acceleration, plus hanging mass multiplied by acceleration. Transpose this on the other side, hanging mass multiplied by G. So acceleration is equal to, okay, anyway, let's just factor this one, MC plus MH. Okay, equal to MH multiplied by G. So this is G. Okay, G. Okay, the target is to compute for acceleration. Okay, so acceleration, okay, divide both sides by MC plus MH. So acceleration here is equal to hanging mass multiplied by G over MC plus MH. Okay, MC plus MH is actually the total mass. So this is the formula for the theoretical value of the acceleration of the cart. Okay, again, so we have this set up. The formula for the experimental value is 2x over t squared. Again, the x is the distance and the time that can be measured using a stopwatch. And hanging mass, okay, this is the value of the hanging mass. Whatever be the mass of this one, that is the value here, multiplied by acceleration due to gravity, which is, in this case, we're going to use 9.8 meters per second squared. Okay, meaning in this one, we need to convert this to, or we can use actually 980 centimeters per second squared. So because the given here is in grams. But if this one is expressed in kilograms, so meaning we need to use the 9.8 meters per second squared. Okay, so let me erase this one. Okay, so divided by the mass total, so that will be the mass of the cart plus the hanging mass. So this is the mass total, mass of cart plus the hanging mass. Okay, so this is the table. We can see here the mass of the dynamics cart. So we can compute or measure the mass of the dynamic cart here using top loading balance. Okay, this is expressed in grams. And then the distance depends on your choice. You can set the distance by group. And here is the hanging mass. Okay, it can be 20 grams or 50 grams. And the mass total, again, to compute for the mass total, we simply add the mass of the dynamics cart and the hanging mass. Okay, so we can get the mass total. And then we need to perform the experiment 3 times. Okay, first trial, second trial, the third trial. Okay, we need to measure the time, and then after that, get the sum divided by 3, and then we can compute the average time. And let's compute for experimental value of acceleration. Again, the formula is 2 multiplied by the distance, okay, whatever be the value here, multiplied by 2 divided by the square of the average time, so we can compute the experimental value of the acceleration. And then for the theoretical, okay, that will be 20 grams, or the hanging mass multiplied by 980 centimeters per second squared divided by the m total, or that is the sum of the hanging mass and also the mass of the cart. Okay, so we can compute the theoretical value. And then percent error, again, theoretical value minus experimental value over the theoretical acceleration multiplied by 100. Okay, again, so we have these are the formulas, or these are the guide. And suppose we have these values. Okay, after measuring the cart using top loading balance, so we measured that the cart has a mass of 517.65 grams. And then we set the distance at 60 centimeters. Okay, so after doing the 3 trials, we came up that the values for the time are 1.79, 1.80, and 1.82. Okay, we need to get the average. Okay, so let me start computing for the experimental value. So to compute for the experimental value, again, the formula is 2x over t squared. Okay, so we need to compute for the average. That's 1.79 plus 1.80 plus 1.82. Okay, divide this by 3. So the answer here is 1.80. So let's use 2 decimal places. 1.80. Okay, this is the time, the average time. So we have the given distance here. Now we can compute the value of experimental value of acceleration. So acceleration is 2x over t squared. Okay, this is 2 multiplied by 60 centimeters. Okay, over 1.80 second square. Okay, this is equal to. So the value of the acceleration here is 37.04. This is 37.04 centimeters per second squared. So this is the experimental value, centimeters per second squared. Okay, now let's compute for the theoretical value. Again, the formula is this one. Okay, so we have acceleration is equal to, so the given mass here, the hanging mass is 20 grams. So 20 grams multiplied by 980 centimeters per second squared, and then divide this by the mass total. So what is the mass total? 20 grams plus 517.65. So this is 537.65. This is the total. Okay, again, 20 grams plus 517.65. This is 537. So over 537.65. Okay, this is equal to 20 times 980 divided by 537.65. So the answer here is 36.45. So this one is equal to 36.45. So I'm going to write here the value of the theoretical value, 36.45. Then after that, let's compute for the percentage error. Okay, so we have 37.04 minus 36.45, and then divided by the theoretical value, 36.45, multiplied by 100. So this is equal to 1.618 or 1.62. So the percentage error here is 1.62. Okay, so this is the last part of experiment number 2. Okay, so number 1, how does the angle of the track affect the tension on the string? This can be answered using this formula. T is equal to mg sine theta. So this is the formula that we derived last time, in which we can see here that as we increase the angle, there will be increase in the value of the sine theta, and then it will result to the increase also in the value of the tension. So we can see here that the tension, or the angle, is directly proportional to the tension. As angle of the track increases, the tension of the string also increases. How to achieve rotational equilibrium in the equal arm balance? So the setup number 2, in which we use the equal arm balance. So this is about rotational equilibrium. And then we computed for torque 1 and torque 2. So for us to achieve the rotational equilibrium, so torque 1 must be equal to torque 2. So torque on both sides of the equal arm balance must be equal. What is the relationship of the hanging mass to the acceleration of the cart? And what is the relationship of the hanging mass to time of travel? Again, so we have the formula to compute for acceleration. So acceleration is equal to 2 multiplied by the distance, okay, divided by the square of time. And then the other formula is using the hanging mass, okay, multiplied by acceleration due to gravity over the sum of the hanging mass and also the mass of the car. Okay, so based on this formula, we're going to relate the hanging mass and the acceleration. So here's the hanging mass. This is the acceleration. So we can see that they are directly proportional. So hanging mass is directly proportional with the acceleration of the car. So meaning as the hanging mass increases, acceleration also increases. While for the other one, which is the relationship between the hanging mass and time of travel. So again, so here's the hanging mass, and then on the formula, so the time is on the denominator. So meaning they are inversely proportional. So the heavier the hanging mass, the shorter will be the time of travel. Okay, last experiment is about conservation of energy. Okay, and then we have two objectives. The first is to verify the law of conservation of energy, and then the second is to determine the relationship between the change in the gravitational potential energy and the kinetic energy of the falling object. So again, in principle, okay, the change in gravitational potential energy is equal to the change in the kinetic energy. So they are equal. So the law of conservation of energy, so meaning we need to get the total energy, and then the total energy in the system should be conserved. It should be the same. So to compute for the total energy, so this is kinetic energy plus gravitational potential energy. So meaning at any point here, after computing the KE and also the GPE, and then compute the total, so the total energy at any point here should be conserved. So it should be equal. So the sum of the GP and the kinetic energy should be always the value of the total energy here. So it should be constant. Here is the setup for experiment number 3, conservation of energy. So what we did in our experiment is actually we did not use the motion sensor. So the motion sensor is a type of sensor that we actually connect to the Explorer GLX to make sure the position and also the velocity of the ball at the different heights and also at a different velocity. But what we did is we just use a stopwatch, and then we drop the ball, and then we measure the time on the different heights. Okay, and then again, so we measure the time, and then given the time, we can compute the v or the velocity at the different positions, and then that can be actually solved using this equation. So the velocity is equal to initial velocity minus gt. So since the ball started at 0 or at rest, so meaning the initial velocity is 0, so the v is equal to negative gt. Again, the time here is the measured time at different positions. Okay, so in here we need to compute for the gravitational potential energy, kinetic energy, and also the total energy, in which the time will be used to compute the final velocity. Again, so the final velocity is simply equal to negative gt. Again, the g here is constant, that is 9.8 meters per second squared, and then the time here is the measured time. And the y here, so what we did is we started at 2 meters. So 2 meters, then 1.8, 1.6, and lower. And again, so given the time, we can measure the v, so that is negative gt, and that v will be used to compute the kinetic energy. So for kinetic energy, so the formula is 1/2 multiplied by the mass of the ball multiplied by the square of the velocity. So the velocity is the one we computed using time. And then, so we have to compare that with the gravitational potential energy. We also need to compute for the gravitational potential energy. And gravitational potential energy is equal to mass of the ball multiplied by acceleration due to gravity, which is 9.8 meters per second squared, multiplied by the value of y. Again, so ano ba, what are the values of y here? So those are the 2 meters, 1.8, 1.6, 1.4, and lower. And then after getting the gravitational potential energy and kinetic energy, so we can actually calculate the total energy. And total energy is simply the sum of the gravitational potential energy and kinetic energy. Again, so the topic here is conservation of energy. So the conservation of the total energy. So in this experiment, so we are expecting the total energy is conserved. Okay, so meaning the total energy at every position, it must have the same value. So it should remains the same. So if that is the case, if they have the same value, so we can see that the total energy is conserved. Example, so we have this ball, okay, assuming that the mass of the ball is 0.0097 kilograms, or that is equal to 0.97 grams. Again, so the 0.97 grams, so we have to convert that to kilograms. So the unit for mass here should be in kilograms. And then suppose the values for y, so it started at 2 meters, and then at 2 meters, so this is where we drop the ball, and then so the time there is time 0, and then so it started at rest, so meaning the at 2 meters, so the initial velocity is also 0. So if this is 0, so Vf will be also 0, and the kinetic energy will be automatic to be also 0, because using the formula 1/2 mv squared, so since the velocity is 0, so meaning the kinetic energy will be also 0. And then for the mg, for the gravitational potential energy, we need to use the formula mgy. So we just multiply the 0.0097 kilograms by 2 meters, and then that is to be multiplied by the height, which is 2 meters, and multiplied by 9.8 meters per second squared. Again, so to compute for this one, okay, so this is simply 0.0097, so this is the mass of the ball, kilograms multiplied by 9.8 meters per second squared, which is the acceleration due to gravity, and then multiplied by 2 meters. Okay, so this one is actually the value of GPE at y1, or 2 meters, and that is equal to 0.1901 joule. Again, the kinetic energy here is 0 because the velocity at that position at 2 meters, so that is actually 0, so that is at rest. So to compute for the total energy, so GPE plus KE, that is equal to PE, and that is 0.1901 plus 0, so the total energy is 0.1902. Okay, so assuming we already measured the time, and then at 1.8 meters, so the time is 0.20, at 1.60 that is 0.57, 0.53 for 1.40, and 0.49 for 1.20, and so on. Okay, so the first thing we need to do is, again, so we have to compute for the velocity at 1.80 given the time of 0.20 seconds. Again, the formula is negative GT, so this is the formula. Again, the G here is 9.8 meters per second squared. So that is simply equal to negative 9.8 meters per second squared, and then that is to be multiplied by 0.20 seconds. So this one is 9.8 multiplied by 0.2. So the answer here is 1.96. Okay, so the final velocity at 1.80 meters is actually 1.96 meters per second. So given the final velocity, we can actually compute the kinetic energy, again using this formula. Okay, so kinetic energy is equal to 1/2 multiplied by the mass, which is 0.0097 kilograms, and then that is to be multiplied by the velocity that we computed, and that is 1.96 meters per second square. So the kinetic energy here is equal to, again, 0.5 or 1/2 multiplied by the mass, 0.0097 multiplied by 1.96 square. So the answer here is 0.0186. So this is 0.0186. So let us use 4 decimal places here. So this is 0.0186. Okay, so that's the value of the kinetic energy. Now let us compute for the gravitational potential energy at 1.80 meters. So that is the given height. Okay, again, so to compute for GPE, so GPE is equal to mgy, and that is 0.0097 kilograms, which is the mass of the plastic ball, multiplied by 9.8 meters per second squared. And then here, the height here is 1.80. So 1.80 meters. So the GPE, or gravitational potential energy, is equal to, so this is equal to 0.1711 kJ. Okay, now let's compute for the total energy again. So total energy is simply the sum of the GPE and kinetic energy. So we need to get the sum of this, and the answer here is 0.1711 plus 0.0186. So the answer here is 0.1897. So this is the total energy at 1.80 meters na height. Okay, so the same thing that we're going to do with the 0.57. So we compute for the final velocity. 0.53, compute also for the final velocity. Same thing with the 0.49. And then after computing for the final velocity, so that will be used in computing the kinetic energy. Again, so the V will be placed here. Again, the kinetic energy is equal to 1/2 mv squared. Okay, so we can answer this one, okay, using this formula. And then also the QPE need to be computed also. Okay, and that is based on the different heights. So that will be 1.60, 1.40, and 1.20. Okay, so after getting all the GPEs and KEs, let us compute for the total energy. Okay, then after that, we need to get the average. Okay, and then the theoretical value here is actually equal to the formula of, or using the burst height or the maximum height, and that is simply mgy1. Okay, so what is the mgy1? The mgy1, based on our data, so that is actually 0.1901, or that is also the total energy, okay, which is also equal to 0.1901. I think this is a 1. Okay, correction. Okay, and then so you have the average. Okay, so that will be, you have to get the sum divided by 10, then you can get the average. So you have to compare the average and the theoretical value. Okay, so that will be average minus theoretical value over the theoretical value multiplied by 100. Again, you need to get a percent error of less than 10. So we have two questions here again. So the first question is, what will happen to the total energy as the ball falls? Okay, so again, so what we did in our experiment is we computed for GPE and also the kinetic energy at different position, and then after that we added the two, and then we computed for the total energy, and then based on our data, so the total energy is actually the same. Okay, so if they have the same value, so meaning the total energy is conserved. So total energy remains the same in every position of the ball at this falls as it falls. So meaning total energy is conserved. And then, so what is the relationship of kinetic energy and potential energy as the ball falls? So what will happen is, as the ball falls, okay, so this is the GPE, okay, started at GPE. At the maximum height, the GPE is actually the maximum value. And then, so the kinetic energy at the maximum height is actually equal to 0 because that is at rest. But as the ball pulls, okay, so what will happen to the height is there will be decrease in the height. And since the formula for the GPE is mgy, so the height is actually directly proportional to the GPE. So GPE will also decrease. And since the ball is going downward, so we can say that the velocity is also increasing. So increasing the velocity will also increase the value of the kinetic energy. So meaning, so in every decrease in the gravitational potential energy, there will be increase in the kinetic energy. So gravitational potential energy is transformed to kinetic energy as the ball falls. As the ball falls, its height decreases, resulting to decreasing GPE, while its velocity increases as well as its kinetic energy. So the GPE is inversely proportional with the kinetic energy. Experiment number 4 is about Archimedes' principle, and it has two objectives. The first is to determine the density of solids using Archimedes' principle, and the second is to determine the density of liquids using a hydrometer and Archimedes' principle. What is Archimedes' principle? When an object is immersed in water, it feels lighter. In a cylinder filled with water, the action of inserting a mass in the liquid causes it to displace upward. In 2012 BC, the Greek scientist Archimedes discovered the following principle. An object immersed in a fluid is buoyed up by a force equal to the weight of a fluid displaced by the object. This is the Archimedes principle. In formula, we can write a formula for Archimedes principle, which is W is equal to rho multiplied by volume multiplied by acceleration due to gravity. W is the weight of the displaced liquid, rho is the density of fluids, V is the volume of displaced fluids, and G, which is constant, that is the acceleration due to gravity. Any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. In formula, Fb, which is the magnitude of buoyant force, is equal to W fluid, or the weight of the displaced fluid. Weight can be computed using this formula. Weight is equal to mass multiplied by acceleration due to gravity. And to compute for the density, density is equal to mass of the object or mass of the fluid divided by the volume of the fluid or the volume of the object. In this formula, we can derive the formula for mass, and mass is equal to density multiplied by volume. So we just have to substitute this equation to the equation for the weight of the fluid or the weight of the object. So weight, which is equal to mass multiplied by acceleration due to gravity, it will become density multiplied by volume. So this is the volume of mass multiplied by acceleration due to gravity. So since W fluid, or the weight of the displaced fluid, is equal to the buoyant force, the final formula to compute for the buoyant force is simply equal to density of the fluid multiplied by the volume displaced and multiplied by acceleration due to gravity. By getting the weight of the object in air and the weight of the object in water, we can compute the buoyant force. Buoyant force is equal to weight in air minus weight in water. From this, we can derive the formula for the density of solid, and the formula is density of solid is equal to weight in air multiplied by the density of the fluid divided by the weight in air minus the weight in water. Now let us proceed with the discussion of the procedure for the first part of the experiment number 4, and that is to determine the density of solids. In this setup, we can see the Explorer GLX, which is connected to the force sensor. The force sensor is used to measure the weight of the metal specimen here. As we can see on the first setup, the metal specimen is in air. So we have to measure the weight of the specimen in air using force sensor, and the reading will be displayed in the Explorer GLX. Again, the reading here is the weight in air. Then after that, we need to submerge the metal specimen in water and measure the weight of the metal sample or the metal specimen in water. And that is W sub W. And then after that, after getting the weight in air and also the weight in water, we can compute now for the density of solid. Density of solid is equal to the weight in air multiplied by the density of water, which is constant, and that is equal to 1 gram per cubic centimeters, over weight in air minus the weight in water. Suppose we have these values, okay, for the weight in air, and that is equal to 0.88 newtons, and then for the weight in water, that is equal to 0.77 newtons. We have to identify the kind of metal sample, and then we should place the name of the material on the first column. The weight in air, or W sub A, should be placed on the second column. The weight in water should be placed on the third column. And to compute for the density or experimental density of solid, we need to use this equation, weight in air multiplied by the density of water over weight in air minus the weight in water. For the theoretical value of the density of the material, we have to look at the table of densities. And then after that, let's compare the theoretical and experimental value. And let us compute for the percentage error. Again, percentage error is equal to theoretical value minus the experimental value. This is absolute value over the theoretical value and then multiplied by 100. The 0.88 and the 0.77 as readings from the Explorer GLX, they are expressed in newtons. But in the table, the answer should be expressed in dynes. So therefore, we have to convert newtons into dynes. And in 1 newton, this is equivalent to 100,000 dynes. 0.88 multiplied by 100,000, it gives 88,000. While 0.77 multiplied by 100,000, this is equal to 77,000. And then for the metal sample, which is brass, the constant value is 8.50 grams per cubic centimeter. Given the following data, let us compute for the experimental value of the density of brass as well as the percentage error. Density of solid is equal to weight in air multiplied by the density of water over weight in air minus the weight in water. Weight in air is equal to 88,000 dynes multiplied by the constant value of the density of water, 1.0 grams per cubic centimeter, over weight in air, 88,000, minus weight in liquid or weight in water, 77,000 dynes. This is equal to 88,000 multiplied by 1 divided by 88,000 minus 77,000. The answer here is 8. This is 8.0 grams per cubic centimeter. So this is the experimental value of the density of brass. Now let us compute for the percentage error. Theoretical value minus experimental value over the theoretical value multiplied by 100. This is absolute value. So we have 8.50 minus 8.0 over 8.50 multiplied by 100. The percentage error is equal to 5.88. 5.88% is the percentage error. Now let us proceed with the second part of the experiment, and that is to determine the density of liquids. In this one, we're going to use hydrometer, and hydrometer is used to measure the density of fluids. We have here the same setup with the first part, but instead of using a beaker, we are using graduated cylinder as the container. We have to measure also the weight in air of the metal sample. We need to submerge the object or the metal sample in the liquid, and we need to measure the weight in the liquid. And after that, we also need to measure the volume of displaced fluid. From that, we need to measure the initial volume and also the final volume. So the volume here is simply equal to the final volume minus the initial volume. So the V here is the volume of the displaced fluid. To compute for the density of liquid, the formula is the weight in air minus the weight in liquid over acceleration due to gravity multiplied by the volume displaced. In getting the theoretical value of the density of liquids, we have to use a hydrometer. The hydrometer should be placed inside the graduated cylinder. We have to look at the lower meniscus. Whatever be the reading on the hydrometer, that is the theoretical value of the density of liquid. The weight in air should be placed on this column. The weight in the liquid should be placed here. The volume displaced should be placed on the fourth column. We also need to identify the liquid, if that is water or any liquid. Experimental density, we're going to use this equation. The theoretical density should be measured using hydrometer, and then we have to compute for the percentage error. Given the following data, let us compute for the experimental value of the density of liquid 1 as well as the percentage error. Density of liquid is equal to weight in air minus weight in liquid over acceleration due to gravity multiplied by the volume displaced. This is equal to weight in air is 205,800 dynes minus 181,300 dynes over 980, which is the constant value for the value of G, then multiplied by the volume displaced, 24.50 cubic centimeter. So density of liquid is equal to 205,800 minus 181,300 divided by 980 multiplied by 24.5. So density is equal to 1.02 grams per cubic centimeter. Now let us compute for the percentage error. This is 1.02 minus 1.06 over 1.06, which is the theoretical value, times 100. Again, this is absolute value. So the answer is 3.77. First question, how do you relate buoyant force to the density of the metal sample? So this can be actually answered using this equation. So this is the equation that we use in solving for the density of solid or the metal sample. And that is density of solid or the metal sample is equal to the weight in air over the buoyant force multiplied by the density of the fluid. So based on this, if we're going to relate the buoyant force and the density of the metal sample, we can see that they are inversely proportional. Again, the equation above shows the relationship between the density of the metal sample or the solid to the buoyant force. So based on that, the buoyant force is inversely proportional with the density of the metal sample. Second question, what will happen to the object if its density is greater than that of the fluid? What will happen to the object if its density is equal to that of the fluid? And what will happen to the object if its density is lesser than that of the fluid? If the density of the object is greater than that of the fluid, so we can have this ratio in which the density of fluid over the density of solid, and that is less than to 1. And then that will result to this relationship in which the buoyant force is less than the weight in air. If that is the case, so the object will sink. But if the density of the object is equal to that of the fluid, so if that is the case, so the density of the fluid over the density of the solid is equal to 1. So meaning the buoyant force is equal to the weight in air. So if they are equal, so meaning this will be under equilibrium. So the object will neither sink nor float, or it will be under the neutral buoyancy. So what will happen to the object if its density is less than that of the fluid? So the density of the fluid over the density of the solid is greater than 1, so resulting to the buoyant force, which has a greater value with the weight in air. So the object will float. So the last question is, how do you relate buoyant force to the density of the liquid? So the equation above shows the relationship between the density of the liquid to the buoyant force. Again, so the numerator, so this is actually the value of the buoyant force. And as we can see here that the buoyant force is directly proportional to the density of the liquid. Again, so meaning if we're going to increase the buoyant force, there will be also, or if we're going to increase the density of the liquid, there will be also increase in the buoyant force. Now let us proceed with experiment number 5, which is linear expansion of metals. We have one objective, and that is to measure the coefficient of linear expansion of some metals. Objects undergo changes in dimension when they are heated. This change in length or area or volume is called thermal expansion. At a given temperature, intermolecular distances are definite. When a body is heated, its molecules vibrate more energetically against the action of intermolecular forces, and the displacement of molecules is increased. Since the average distance between the molecules increases, the dimension of the body increases. Consequently, body expands. Expansion in length of solid bodies on heating is called linear expansion. The increase in length per unit original length per Kelvin rise in temperature is called as the coefficient of linear expansion. To compute for the coefficient of linear expansion, we can use this formula. Alpha is equal to delta L over L naught multiplied by delta T. The alpha is called the coefficient of linear expansion. Delta L is the elongation or the change in L. This is LF minus L naught. L naught is the initial length of the metal sample. Delta T is the change in temperature, so we have to know the final temperature and also the initial temperature. The unit for the coefficient of linear expansion is 1 per Celsius degree, or Celsius degree to the -1. This is the setup for experiment number 5, linear expansion of metals. This is called the linear expansion apparatus. We use a steam generator as the source of heat, rubber tubing, Explorer GLX, and then attached to the Explorer GLX is the temperature sensor. We can actually compute or measure the elongation or expansion by just looking at the gauge here. So whatever be the reading here, that is the expansion or the volume of delta L. And then we can collect the excess water using the plastic container. We have to measure first the initial length of the metal rod, and that should be placed on this column. And then we need to be familiar also with the kind of material, if the metal rod is brass, copper, or aluminum. We also need to measure the initial temperature of the metal rod, and we have to place that on this column. The steam flowing from the steam generator going to the linear expansion apparatus will cause the metal rod to expand. And that expansion can be read on the gauge connected to the linear expansion apparatus. Expansion is expressed as delta L, and we also need to measure the final temperature of the metal rod. Initially, we have to set the gauge at 0. After elongation, the reading will be like this. This is the value of delta L. And then again, so whatever be the reading here, we have to divide this by 1000. And that value should be placed on this column for delta L. And then for the final temperature, we have to place that there. In the Explorer GLX, we are setting minimum and maximum value. So the minimum value is actually the initial temperature, and the maximum value is the final temperature of the metal rod. So we have to place here the initial temperature, and then in this column, the final temperature. Again, the minimum temperature is the initial temperature, and the maximum temperature is the final temperature of the metal rod. We can compute delta L using this equation, LF minus L naught, or in this formula, we can compute the final length. So final length is simply L naught plus delta L. And for the change in temperature, final temperature minus the initial temperature. And to compute for the experimental value of the coefficient of linear expansion, alpha is equal to delta L over L naught multiplied by delta T. The delta L is here on this column. L naught is computed on the second column, while delta T is on this column. The theoretical values can be found on the appendix part of the manual. You have to identify the kind of material, and then from that, you just have to copy the value of the theoretical value of the coefficient of linear expansion. And then after that, compute for the percentage error. Given the following data, let us compute for the coefficient of linear expansion of brass. So the specimen here is brass. L naught is 45.5 centimeters. Initial temperature 26.8 degrees Celsius. final temperature 83.5 degrees Celsius, and delta L, which is elongation, 0.044 centimeters. Coefficient of linear expansion is equal to delta L over L naught multiplied by the change in temperature. So delta L is equal to 0.044 centimeters over L naught, 45.5 centimeters, multiplied by the change in temperature. This is 83.5 degrees Celsius minus 26.8 degrees Celsius. This is equal to 1.71 times 10 to the negative 6 per Celsius degree. Or this can be also written as, by moving one decimal point going to the right and changing the exponent, 17.1 times 10 to the negative 5 per Celsius degree. So this is the value of the coefficient of linear expansion of brass. Let's compute for the percentage error. So we have to look at the constant value for the coefficient of linear expansion of brass, and then we have to use this equation: theoretical value minus the experimental value over the theoretical value multiplied by 100. So there are two questions for experiment number 5. The first is, how do you relate change in temperature with expansion of metals? And how do you relate change in temperature with the coefficient of thermal expansion? So in this one, we have the formula for the coefficient of thermal expansion, and that is equal to delta L over L naught multiplied by delta T. So we're going to derive the formula for the change in temperature. So that is simply delta L over alpha multiplied by L naught. So in this formula, we can actually relate the change in temperature with the expansion of metals. So here is the change in temperature. This is the expansion of metals, so we can see that they are directly proportional. So change in temperature is directly proportional with the expansion of metals. And in terms of the change in temperature with the coefficient of thermal expansion, we can see that this is again the change in temperature, and then this is the value of the coefficient of thermal expansions. So we can see that they are inversely proportional. So the second question is, what causes the expansion of metals when heated? So this is actually answered in the theoretical part of the manual. And when a body is heated, its molecules vibrate more energetically against the action of intermolecular forces, and the displacement of molecules is increased. So since the average distance between the molecules increases, the dimension of the body also increases. So consequently, body expands.